some of the major techniques which are used in order to compress images. Okay. Okay, do I? Okay. Okay. Well, the first and the most obvious, but it's really kind of bad thing to do, is subsampling, which is that you actually take out a lot of the information. Okay. As you see here, what we have here is a picture of a little plant, maybe, which has got some detail, got the yellow here, the green, etc., the red, and that produces the image. We could produce it, and therefore reduce by a long way the amount of data by having bigger blocks and averaging the values inside the blocks. Okay, so for this image here, you see where it's got two dark greens, one light green and a blue, it decides, aha, I will make that dark green. Okay, so you see, so this image here goes to that one there. Okay, similarly, things like this part here, which is the reds and the greens, that just basically becomes turned into a single green. So that is what is called subsampling. Okay, that's the quickest and easiest way to reduce the data inside an image. Another way is what is called quantization. Okay, this is what is done when you are converting images into GIFs. Okay, a GIF can only have 255 colors maximum. Okay, so what it does is it looks at the image, the original image, and here you see kind of almost continuous colors, although here it's not perfect, as you see, it's kind of thing. And then it actually says, I will only have half of these colors, and anything whichever one your color is nearest will be transferred to the other color. Pardon me. So instead of having all the various shades of blue, you have a much reduced set of blue colors, and you then work out which color any one of these ones is nearest to. The difference between this one and the previous version, the difference between that one and this one, is that it's still pixel. On the quantization, it was only pixel by pixel, one pixel, one pixel. Here, I'm actually averaging one pixel to one pixel as previously 4 pixels of the previous. Okay. Okay. Well, I'll go through this very quickly because you know all this anyway. So this is the decimal number system is what we use obviously to count with. Okay. And that is based in kind of thousands, hundreds, tens, and units. But is the binary system we use for a computer, and that is why we have 3 bytes of color. Means up to 255, is because that means in each byte there are 8 bits, and 8 bits can come to a maximum of 255. So if it's like 128 and 64, 32, 16, 8, 4, 2, 1, all that together equals 255. And the smallest of that is 0, 0, 0, 0, 0, 0, 0, 0, and that is 0, of course. Okay, so that's how we have 256 values for each byte. Okay. Let's go on next. Now, have any of you ever created web pages? Produced web pages? Yeah. Typically in a web page you'll see something like BG color equals, followed by something like this, hash 00FF00. What color would that be? No. Hang on, you were right. I'm sorry. Yes, it is right. It is. Just tell the others why is it that it's green?
The two, the first two bits represent R, and the second two represent G, and the
That's right. Exactly. Yeah, that's right. So that 0, 0 represents the red, FF represents the green, and 0, 0 represents the blue. Okay. So why does so what does FF? What is the value of FF?
255.
That's right, exactly. Okay, you all know. I think you must all know hexadecimal, do you? You know that basically hexadecimal is, whereas binary has units of 1 or 0, decimal has units of 0 to 9. Hexadecimal has 0 to 15, and 15 is represented as F. Okay, so so basically, when you say FF, you mean 15 times 15 15s plus 15. Okay, which equals, of course, 255. Okay, it's just a convenient way that we use to represent color. Okay, and you'll see that on virtually every web page, is how you can actually use these numbers to represent the colors of the red, green, and blue. Okay, so won't labour this point too much. Okay, these are just so the hexadecimal and RGB values of very typical colours there. Okay, so now let's just have a let's just do a new here. Okay, so I mean, if the way we represent pictures is basically it is sequences of dots. So if I do some, sorry, these are not very good. So if we do the letter T, okay, that is, I mean, I can represent that by a sequence of dots, okay, and then for each square there can be a color, okay, inside that object. Now, for example, on this image, you have it was kind of 5 by 5. No, sorry, I'll put this to. I don't know how to put that to the back. Okay, let's do a new slide. Okay. Oh yes. Let's just delete that. Oh, how do I delete it? No, I can't delete it. All right, I'll just start again. Okay, but if you have an image which is 5 pixels by 5 pixels, okay. So if we have 5 by 5 pixels, how many bytes would it take to represent that in terms of full color? If I want, so I've got 5 by 5, okay. So I've got an image which is 5 by 5. So I've got 1, 2, 3, 4, 5, 1, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay, got an image of 5 by 5. Okay, and each pixel can have its full color. So how many bytes do you need to be able to produce all the colors the human eye can see? How many bytes per pixel? How many? Well, it's 3. So it's 3 bytes per pixel. So 5 by 5, that's 25. That makes 75. 75 bytes altogether. Okay. So now, so that's kind of 5 by 5, which will be tiny, wouldn't it? They'll be absolutely small, very, very small. So if we had it something more like 100 by 100, okay, how many, and that has 3 bytes per pixel as well. That effectively means that it would take, that's 10,000, 30,000 bytes, which is how many K? 30. 30, which is 30K, okay, and that's 100 by 100, okay, which on this screen, I mean, it's not very large. I mean, how big is a typical computer screen?
15,
No, in terms of pixels, sorry.
800 by 600.
Yeah. If, you know, even if older ones are kind of 800 by 600. So if we work that again, so 800 by 600, that's, my God, how much is that? Oh, no, 600. It's like 48. That's naught.
480,000.
That's right. Thank you very much. 480,000. 480,000. So that is 480K. Okay, for a 800 by 600. And of course, on a much larger screen, 1024 times 786 equals, well, that'll be much higher still. So that'll be something like, it's about bound to be approximately 800K. Okay, so that's how much space we need. So now, think about, well, of course now everybody has broadband, and so therefore, well, a lot of people have broadband, so it makes it very easy to transmit quite large things very quickly. But it's still, as you can see here, these are very large amounts of data, okay? And so what, typically, do we send kind of images like that? Would typically an image this size, would it be 800K if we got it off the internet? No. So it is compressed, exactly. So therefore, because these things are just so large, we need to have compression. Okay. Now there are basically, well, I'll be coming on to this shortly. Okay. There are two forms of compression typically used in image compression. One is called lossless, and the other one is called lossy. Okay. Typically, which form of image compression uses lossless? Which kind of type of file uses lossless compression?
Text.
No. No, I'm just talking about proper image files.
Okay, image file.
Image files, yes. I'll just close this door.
GIF.
Yes, exactly. GIF files are typically lossless. Okay, although they only have 256 colors, the compression that you do does not actually remove any information from the image. Okay. However, if you use JPEG, which is lossy, what it does is it actually tries to eliminate information in the image which it believes your eye cannot see. Okay, that's the big difference between the two forms. Because as you see, I mean, if it takes 800K to represent a full screen, and if you think that, you know, typically digital video will be having 25 frames per second, the amount of data that you would have to transmit is absolutely enormous. So therefore, that is why techniques of compression have emerged. Okay. Now it's maybe not so important as it used to be because of things like broadband, but in times when you only had modems, it was really important that compression was working. Okay, so let's go forward.